Hello, and welcome to this web seminar on Microchip's LLC Resonant Converter reference design. My name is Alex Dumais, and I am a Senior Applications Engineer in the High Performance Microcontroller Division of Microchip. In this webinar, we will start with some background information on resonant converters and why resonant converters are gaining interest. Then we will discuss different resonant converter topologies with an emphasis on LLC resonant converters. Afterwards, we will go through the design of Microchip's 200-watt LLC resonant converter reference design. So let's get started with some background information on resonant converters. With the push for higher efficiency converters, power supply designers are looking for different topologies to improve their power supply efficiency. One such topology that has been gaining interest is the resonant converter. Until recently, resonant converters have been overlooked due to their complexity of control. The dsPIC digital signal controller, with its advanced peripherals and high-speed DSP engine, provides the capability to easily control complex systems such as resonant converters. Let's look at several advantages of the resonant converter topology. Resonant converters are becoming more and more popular these days due to their ability to achieve high efficiency through softly commutating the switching devices. Soft switching techniques such as zero voltage switching and zero current switching can be implemented, which provides better EMI performance along with higher efficiency. Resonant converters are capable of achieving high power density, meaning the overall converter size can be reduced as the converter can operate at higher switching frequencies due to the soft switching described above. Resonant converters are well suited for high power applications. They also work well over a wide input voltage range. Resonant converters have lower cost due to their higher switching frequencies, as the size of passive components can be reduced. This slide demonstrates a high level the architecture of any resonant converter. A resonant converter can be divided into four main blocks: the full or half bridge converter, a resonant tank, a rectifier, and a low pass filter. Starting on the input side, the full or half bridge converter is typically configured complementary mode with a fixed duty cycle and with some dead time. The bridge converter is typically operated by adjusting the duty cycle, but in the case of resonant converters, the bridge converter is frequency controlled. This means that by changing the frequency of the converter, we change the impedance of the resonant tank. We will discuss more on this at a later time. The output of the bridge rectifier is a square wave with a fixed duty cycle, an amplitude equal to the input voltage, with a DC offset of the input voltage by 2. The resonant tank is made up of reactive components, capacitors, and inductors, and can have several different configurations. Depending on the tank configuration, the output will have either a sinusoidal current or sinusoidal voltage. The resonant tank will introduce a phase shift between the voltage and the current, and because of this, we are able to achieve soft switching. Combining the bridge converter and the resonant tank, we create a resonant inverter, and by adding a rectifier and low-pass filter, we create a resonant converter. Before we dive any deeper into resonant converters, we should first understand a couple terms that are commonly used to describe resonant converters. So first, let us look at the meaning of resonance. In a simple series LC circuit, shown in the bottom right, there exists a point where the reactance of the capacitor and the reactance of the inductor are equal in magnitude but opposite in sign. At this particular frequency, the reactance is 0, and the impedance between the input and the output of the circuit is at its minimum. If we look at the impedance versus frequency plot, we will see that the summation of the capacitor and inductor reactance is at its minimum at the resonant point. Another term used to describe resonant converters is quality factor. Quality factor, or Q, is a dimensionless parameter that describes how damped a resonant circuit is. The higher the quality factor, the narrower the bandwidth of the system. As a general definition, quality factor can be defined as the ratio between the power stored and the power dissipated in a circuit. It is important to note that quality factor changes with load, i.e., it is not a fixed parameter. We will see more on this later. As discussed earlier, resonant converters are able to achieve high efficiency from employing soft switching techniques. Following slides discuss what these soft switching techniques are and their advantages. Following animation demonstrates zero voltage switching. First, the drain to source capacitance of the MOSFET is discharged. Next, the PWM enables the MOSFET, allowing the current through the MOSFET to begin to rise. When the PWM is disabled, the drain to source voltage begins to rise, but the current still flows through the MOSFET. From this animation, we can see that at switch turn-on, we are eliminating the MOSFET switching losses, as the voltage across the drain to source is zero. This is referred to as zero voltage switching. At switch turn-off, we see that there will be a significant amount of current and voltage at the transition state, which translates into switching losses. Zero voltage switching is preferred in high voltage, high power applications. The following animation demonstrates zero current switching. First, the PWM is enabled and the current through the MOSFET begins to rise as the MOSFET's drain to source voltage drops. Once the current through the MOSFET becomes zero, we disable the MOSFET. Now the drain to source voltage begins to rise. This is the point at which zero current switching occurs. From the animation, we can see that at switch turn-off, we are eliminating the MOSFET switching losses, as the current is zero and the drain to source voltage is also zero. At switch turn-on, we see that there will be a significant amount of current and voltage at the transition state, which translates into switching losses. Zero current switching can be implemented at switch turn-on as well as switch turn-off. With soft switching, we can reduce the noise in the system, therefore improving EMI performance. Next, we will take a closer look at three different resonant converter topologies. For a series resonant converter, the resonant tank is composed of inductor LR and capacitor CR in a series configuration, as shown in the schematic. It is called a series resonant converter because the resonant tank is in series with the output load. Here, the resonant tank and the output load act as a voltage divider and therefore limit the gain of the tank to be less than or equal to 1. Looking at the voltage gain curves on the bottom right diagram, we see that all Q curves intersect at resonant frequency point. From the voltage gain plot, we can also see that the converter operates closer to resonance when the input voltage is at low line. For zero voltage switching, the converter must work at or above resonance. For a parallel resonant converter, the resonant tank is similar to that of the series resonant converter, but now the output load is connected in parallel with the resonant capacitor, CR. Similar to the series resonant converter, the parallel resonant converter will operate closer to resonant frequency at low line, and for zero voltage switching, the converter should work at or above resonance. Unlike the series resonant converter, the parallel resonant converter can operate at no load. But one disadvantage of the parallel resonant converter is that it will operate with high circulating currents, even in no load conditions. Series parallel converters are a combination of the series resonant converter and the parallel resonant converter. Here we are showing an LLC resonant converter, which is composed of two inductors and a single resonant capacitor. Another common series parallel resonant converter is the LCC converter, which replaces the inductor LPR with another capacitor, as in the case of the parallel resonant configuration. LLC resonant converters have many advantages. They can operate at resonance at nominal input voltage. They can operate at no load conditions. They have a lower circulating current than the parallel resonant converter. The advantages of resonant converters are their ability to operate over a wide input voltage range, and the fact that ZVS and ZCS is achievable over the entire operating condition. Next, we will examine the different operating modes of an LLC resonant converter. First, we will start out by examining in detail the operational waveforms when the system operates at resonant frequency. For simplicity, we are showing a half-bridge converter on the primary side and a full-wave rectifier on the secondary. Diodes D1, D2, and capacitors C1, C2 have been explicitly drawn here, but are essentially part of the MOSFET's parasitics. At time t is less than T0, the bottom MOSFET Q2 is conducting, and diode D4 is in forward biased. The voltage drop across capacitor C1 is equal to the input voltage. At time t is less than T1 but greater than T0, both MOSFETs are disabled. This is known as dead time region, and both secondary diodes, D3, D4, are reverse biased. At this time, the output capacitor is supplying the required load current. On the primary side, we see that the magnetizing current is flowing and will begin to discharge capacitor C1 and charge capacitor C2. Magnetizing current must be large enough to charge and discharge the capacitors before the dead time interval ends. At the time interval t is less than T2 but greater than T1, the high side MOSFET Q1 begins to transition to the on state. Initially, the magnetizing current is negative, and the internal body diode of the MOSFET will be forward biased. Diode D3 is also transitioning to forward bias. When MOSFET Q1 is enabled, the drain to source voltage is 0. Therefore, 0 voltage switching is obtained. At time t is less than T3 but greater than T2, both MOSFETs Q1 and diode D3 are conducting. This is the first interval in which power transfer takes place. The tank current is supplied by the input voltage source, and the magnetizing current is generated by the secondary voltage reflected back to the primary by the transformer turns ratio. Magnetizing inductor is clamped at this voltage, hence the linear rise of the magnetizing current. The sinusoidal tank current flowing in the transformer will generate a quasi-sinusoidal current on the secondary side, related by the transformer turns ratio. At the end of the switching cycle, current flowing through diode D3 will be equal to 0. Hence, 0 current switching is achieved on the secondary side. At the time interval t is less than T4 but greater than T3, the primary current is the magnetizing current. Circuit operation is the same as the previous dead time interval, except now capacitor C1 is being charged while capacitor C2 is being discharged. Circuit operation for the remaining time intervals will be the reverse of the first half cycle. Now that we have reviewed in detail the circuit operation at resonance, we will review the differences in circuit behavior when the converter operates above and below resonance. When operating below resonance, the tank fundamental sine wave will have a shorter period than that of the switching frequency. A decrease in the switching frequency is an increase in the switching period. From the figure, we can see that the tank current will equal the magnetizing current before the half period ends, Tx to T3 transition. From this point, the current flowing in the primary is that of the magnetizing current. Circuit behavior is somehow reversed compared to the operation below resonance. Since the resonant period is longer than that of the switching period, at the end of the switching half period, the tank current is higher than the magnetizing current. During the dead time interval, the tank current falls rapidly to the value of the magnetizing current, so that a new half cycle can start. Now that we have some background information on resonant converters, we can proceed with looking at Microchip's 200-watt LLC resonant converter reference design. The LLC resonant converter reference design is rated for 200 watts with the nominal input voltage of 400 volts DC. This LLC reference design is intended to be the second stage in an AC-DC application, so the nominal input voltage is the typical output voltage of a PFC converter. The ability of the LLC converter to operate over a wide input range allows the bulk capacitors on the PFC converter, the required for holdup time, to be reduced. As this design is 200 watts, the half-bridge converter was selected for driving the resonant tank. As for the rectifier, the traditional full-wave rectifier was replaced with a synchronous rectifier circuit, where MOSFETs replace the diodes, to improve overall efficiency. High voltage isolation, separating the primary and secondary, is obtained through proper component selection and magnetic structures. Use of this reference design is royalty-free, and complete documentation, software, and hardware design information is available on Microchip's website. Demonstration units are also available from worldwide Microchip sales offices. This slide shows a system-level block diagram of the LLC resonant converter. A single dsPIC 33F GS series digital signal controller, shown in the center of the block diagram, drives the power stages, half-bridge converter, and the synchronous rectifier, performs control loop operations, power management communication, and fault management routines. Now that we have seen a functional overview of the LLC resonant converter, we can physically locate all sections on a picture of the reference design itself. This is a top view of the LLC resonant converter reference design. Positions of each block of the system are highlighted as follows. The input terminal can be seen on the bottom left and the output terminal on the top right. The half-bridge converter can be found towards the upper left side. Synchronous rectifier is located on the top right. Output filter is located in the middle right-hand side. Flyback auxiliary power is located on the bottom left-hand side. And lastly, the dsPIC DSC is located on the bottom right of the board. Next, we will look at the operation of the half-bridge converter and the resonant tank. A circuit diagram of the half-bridge converter and the resonant tank is as shown. Two MOSFETs are connected in a bridge configuration. The resonant tank is connected at the half-bridge point. The half-bridge converter is configured in complementary mode with a fixed duty cycle and with some dead time. This dead time serves two purposes. First, it prevents shoot-through, both MOSFETs on at the same time. Secondly, it is the time interval used to charge and discharge the MOSFET's drain-to-source capacitance, which is used for zero-voltage switching, as seen earlier in this presentation. Because of the high switching frequencies, MOSFETs are preferred over IGBTs. Resonant capacitor blocks the DC component of the square wave, producing a signal that is centered around 0 volts. The resonant tank will filter the higher harmonics, essentially only allowing sinusoidal current to flow. Next, let's look at the rectifier block found on the secondary side. There are three different rectifier topologies to consider: half wave, full wave, and bridge rectifier. As this application has a low output voltage and high output current, the bridge rectifier is not a suitable solution. For this reference design, we have used a full wave rectifier, but we have replaced the diodes with MOSFETs. This is more commonly known as synchronous rectification. The MOSFET switching losses and the conduction losses are less than that of the diode's losses, which helps improve overall efficiency. MOSFETs have been placed on the low side, which are ground referenced, to reduce component count and complexity. One thing to note is that now that we have added MOSFETs to the rectifier, special care must be taken to maintain zero current switching. Let's now look at the auxiliary flyback circuit. Here is a high-level block diagram of the auxiliary power section. In this design, we were targeting high efficiency and very low power at no load operating conditions. To do this, the auxiliary circuit has been designed with an auto shutoff feature, providing low standby power. The circuit also provides the ability to restart the auxiliary circuit in the event of a fault condition. Upon system startup, the flyback converter provides power to the dsPIC. When the dsPIC is up and running, the output from the LLC converter, which is 12 volts, will provide the necessary power for the dsPIC, essentially powering itself. Next, let us recap what we discussed on resonant converters. In this webinar, we discussed the different resonant converter topologies, operational waveforms of LLC resonant converters, Microchip's 200-watt LLC resonant converter reference design. From our discussions, we saw that the LLC resonant converter is a suitable DC to DC converter for high power applications with its high efficiency, high power density, and its ability to operate over a wide input voltage range. Thank you for joining me in this webinar on the LLC resonant converter reference design using the dsPIC digital signal controller. Please visit the link on the page for more design details on the LLC resonant converter, as well as other switch mode power supply reference design. Thank you.